Hi, everyone. Today we're going to be talking about waves and sound. Now, there are two types of mechanical waves. Mechanical waves are, first of all, the type of waves we're going to be studying in this unit. Mechanical waves require a medium or something to move through. So the waves can move are based on the movement of the particles that the waves are moving through versus the wave motion itself. So you see here on the screen, we have a transverse wave and a longitudinal wave. We're going to explain more about those later in this video. Now, the wave that you see at a sporting event is very similar in a lot of ways to mechanical waves in general. The particles or people move up and down, okay, as the wave passes through them. But the people themselves don't translate or move from one place to another. And that's what happens with every type of wave. It's a way to move energy from point A to point B while leaving the bulk of the material that it's moving through behind. Okay. So, like I said, we're going to be talking a little bit about the direction of travel of the wave versus the way the particles move. Okay, so the first wave we're going to talk about is a transverse wave. And what we have here is that equilibrium position that would be where, like, the people in the stands would just be sitting if the wave wasn't happening. Okay. Now, this transverse wave has the particles moving up and down while the wave is traveling either left or right. In other words, transverse means the wave motion is perpendicular to the particle motion. Now, when we're trying to discuss waves, we're going to need to get some vocabulary. So the vocabulary we're going to want to address is first of all, the concept of a crest or the peak or the maximum height above the equilibrium position, okay, versus a trough, which would be the minimum, okay, the height below the equilibrium position. We refer to the amplitude as the displacement away from the equilibrium position. So you can have a positive amplitude relating to the crest or a negative amplitude relating to the trough. Right. What I've highlighted here are one full wave. One full wave goes from the position, the location on one wave until that exact same location on the other wave. You have to have the full disturbance. So it could be from trough to trough, from equilibrium through a crest, through a trough back to equilibrium, or from crest to crest, or any two of the same exact positions on two consecutive waves. So that's how long or what is one wave. Okay. What we have diagrammed here is one wavelength. The symbol that you see is the lambda. Okay. And lambda just looks like, I kind of think of it as a T-Rex with no arms, or like a guy running with no head. I don't know. It's just weird, but it is a Greek symbol for the letter L as in length. Okay. In comparison, we have the longitudinal wave, which has both a series of compressions and what we call rarefactions or spreading out of the wave. And those are effectively like a wave trough. And in a longitudinal wave, the wave motion is in the same direction or parallel to the motion of the particles. Okay. So again, getting back to our transverse wave is generally the way we are going to be diagramming and thinking about all of our wave motions, just from a point of view here. Now, the period is the amount of time it takes for one full wave to pass a specific location. Period is always given in time units of seconds. Frequency is the number of waves that pass in a given amount of time. In other words, it's it's a per second or 1/seconds, which is known as a hertz or symbolized, abbreviated as Hz. Velocity, this is back to August, back to the beginning, is the displacement over the time. So In wave motion, okay, we're going to have one wave pass, or one wavelength, over the amount of time it takes for one wave to pass, which would be period. A more convenient way of talking about this, because generally speaking, when we're talking wave motion, we're talking periods that are incredibly brief, okay? Really, really small, most often less than 1 second. So in those cases, it's way more convenient to use the concept of frequency. So the equation of velocity for every single type of wave out there is that velocity is equal to the frequency times the wavelength. Now, okay, the actual value of the speed of the wave, what this velocity is going to be equal to, is determined by the medium being the stuff through which it moves through. Okay. All right. And we're going to start with water waves, because usually these are the types of waves people think of first of all. And let me just tell you this: water waves are, the speed of the wave is determined by the depth. However, water waves are like super, super, super complicated. So we are not going to be doing any equations related to water waves. Just know that the deeper the water, the faster the wave is going to be. Okay. So we can use the generic general equation, V equals frequency times wavelength, for water waves, but we're not going to be worried about the depth of the water to actually calculate what that value will be, and then go from there. However, we also are going to be interested in waves on a string, like any musical instrument, or if you've ever played telephone using the tin cans or something and a string connecting them. In this situation, it has to do with the tension. Okay, so the velocity is equal to the square root of the tension divided by something called the linear mass density, which is also known as the mass per length of a string. Okay, you can substitute it in as the individual mass of the string and the length of the string, or as a whole quantity, the linear mass density, which would be given in kilograms per meter. Okay. The last type of medium that I am going to introduce you to right now and ask that you think about and work with is the velocity of sound in air. This is something really important to think about, because sound is going to typically be our longitudinal wave. Most of the waves you think of are probably transverse, but sound is a longitudinal wave. Sorry, that's a U, not an I. You don't need to dot a U. You do need to dot the I over here. So in sound and air, what the actual velocity depends on is the temperature of the air. The hotter the air, the faster the sound is going to move. Just so you know, we are typically going to assume a 20-degree situation, which is a pretty standard, it's a cool room, but it's a reasonable room temperature. And if it's 20 degrees, the velocity of sound in air is 343 meters per second. That information is on the back of your equation sheet, but you can get that here. Now, that's going to conclude what we're doing today. Please work on the homework that's assigned on MyHB.